So it is my great pleasure to welcome to the Michigan MassTimber Community of Practice, Dr. Dan Tingley to share some of his insights and experiences designing mass timber bridges.
Welcome. Good morning, ladies and gentlemen. It's great to be here. Again, my name is Dan Tingley. I'm in Jacksonville, Florida right now at our office here in Florida. And, when I grew up in Eastern Canada, in that circle there up in Canada, you can see it. I grew up in New Brunswick, a little province in Eastern Canada with high tides and great lobster. If you're ever up that way, you'll know about it. And in the New Brunswick, it has kind of a great distinction in that it has the longest covered bridge in the world. And back in the early 1900s, late 1800s, the Eastern European designers that come over and settled the country, St. John, New Brunswick, where I grew up, is the oldest city in North America. And of course, they had to get across the gap. At the end of the day, they knew something. And that is that if they built their howe trusses out of spruce and put a cover on them, they lasted a long time. And some people think that covered bridges is a place to go to kiss your girlfriend or yell echo or some other method, but that isn't why we build covered bridges. We build covered bridges to keep the water off the joints so that these untreated howe truss bridges can go hundreds of years. And so that's how MassTimber got me started, designing buildings like this, 3-pin post and beam, queen hammer truss as a interpretive center for the early Scots that settled way back in the day, hundreds of years ago. And of course, MassTimber had this kind of look to it and touch and feel. When I was cutting my teeth in the late 60s, early 70s, and took my first undergraduate degree in forest engineering, designing these buildings here, as you can see, with pins and so on, and stress curves was the state of the art back then to bring stability to a large dimension timber, boxed in heart, so that it didn't twist and cup and wow and put stress on the joints. Later on in my life, as I got a little bit better at engineering in the 80s, this was my addition to MassTimber. This is a 535-foot clear span, 14-story high, barracks type dome in northern New Brunswick. We're for coal storage because we just knew SO2 issues made steel just an unsuitable choice. And this was our MassTimber idea back in that day in the 80s, as you can see here. With the inside barracks dome, and what are we storing in there? Coal or potash or those sorts of things in our large, very large glulam beam and glulam deck or solid sawn deck buildings, which we called MassTimber. Of course, you can see Superior Dome here. You folks very familiar with these sorts of things in Michigan. Very large timber domes, which we, back in the day in the 80s and 90s, we called our MassTimber Tacoma Dome. As you can see, very big buildings, all built, of course, with timber. And sometimes I think we forget about these old buildings that set the precedent back in the day for timber, as you can see here in the University of Portland. Now, these great old buildings gave way to the 90s as we started to get a little bit more inventive with our strategies for curving and bending beams, as you can see here in these beautiful, aesthetically pleasing buildings that made bold statements about timber and, of course, using timber in things like swimming pools, where steel just didn't do the job as well because, of course, corrosive environments in timber just doesn't rust, as you can see here. Or this one I was involved with in Vienna called the Wave. This one here, only in Vienna did the oil money have enough money to make a wastewater treatment facility look like this. This is a high-strength fiber reinforced S sinusoidal shaped glulam beam I designed in Vienna back in the day. Or another one here, big playground equipment building. Again, what our vision of MassTimber was in the 90s now as we work along in high strength fiber. You can see me bending over doing some QA on a RP layer in there. I had brown hair and more of it, as you can see. Now I got a bad case of gray hair and loose hair. So I'm, just getting older as the days go by. But these bridges and buildings you can see here are just getting more and more extensive. This is the largest glulam beam in Europe, built with a blowdown wood. When we had the high winds would go through and they were burning pyres of beef back in the day at McDonald's. McDonald's wanted to make an environmental statement. So in 99, we built these huge beams with high strength fiber out of blowdown wood. It was all micro-checked and shear. And this is one half of a beam. And we parked one half of a beam across the Autobahn, and we said McDonald's building with blowdown wood, and parked 10 smart cars in front of it and put the building up in 8 days because we wanted that increased speed of being able to assemble building a roof system in place. This is where the old Pope was born in Krakow, Portland, where we double curve glulam beams. We curve them one way, rip them, then curve them another way and make them out of high strength fiber and Eastern spruce. So mass timber kind of come along now in the last 10 to 15 years in a more effective way. And engineered wood products have arrived on the scene. And with this arrival, of course, is a whole level of interest that was not there in the decades past. CLT, as you can see here, basically a cross-laminated timber, similar to plywood, but made with much thicker, of course, the solid sawn elements, to mate together with the glulam beams, as you can see them here. The traditional mode of being able to build a structure, lightweight compared to steel and concrete. We can prefabricate components, and of course has environmental advantages such as renewable and low carbon footprints. And the mass timber structures take on many forms now, as we can have nail laminated timber, we can have dowel laminated timber. We put them together with glulam beams and form up wall systems and post and beam systems, of course, which allow us to build more effective structures that are aesthetically pleasing. You can also add LVL with a cross ply every non-clam, or you can have MPP, mass plywood panel, or the old guard Paralam, as you can see here, the LSL, SSL, and various forms of strand lumber to go with the plywood. So these all form the innovations of the past 100 years, working up to more recent, as I said before, as CLT. And this whole selection of timber products and opportunities mean that we're able to enter marketplaces where we weren't entering before, such as high-rise buildings, as you can see here. So this is what we now know as the mass timber. But what we really don't know is that mass timber has moved on into the bridge side, and that's why I'm here today to talk about just that. As you can see here, this mass plywood panel deck and post-tension glulam girder superstructure system built in harm's way. This bridge is topped 5 times a year in Australia. This bridge was built in Jefferson, Oregon, designed by the team in Jefferson, Oregon, shipped halfway around the world and assembled and erected on site. Everything was pre-machined, post-treated, and a design life of 100 years. Why was it used? Well, concrete in this particular case was going to overload the existing substructure so that it couldn't be reused. So timber was lightweight. Just how much lighter weight? In this particular bridge, the weight of the timber option was 1/5. I'll say that again, 1/5 the dead weight of a cast in place option and 1/15 of a concrete total super and deck option. And of course, that's significant when it comes to reusing old superstructures, as you can see here in this MPP deck system with a transverse diaphragm, what we call a curtain girder superstructure in here, and of course a through rod that allows us to post tension. Why are we doing that? Well, we've got to withstand floods, and the debris fields can be 4 or 5 feet high that hit the side of this bridge and hit it 5 times a year. So we want a thin profile. They don't install a TL4 truck crash proof guardrail system. They want the river to top the bridge. They want the debris field to get by it. As you can see in here, this provides for a typical new mass timber type bridge system, all pre-machined, pre-assembled. This bridge was completely pre-assembled in the plant before disassembly, treatment with copper naphthenate in an oil-based solvent. Of course, you could not use the water-based solvent in this particular case because the water-based solvent in typical treatments like CCA or AZQ will swell the wood and distort the location of all the bolt holes and make it impossible to assemble on site later on. And so they're treated with an oil-based solvent and a reactive agent that fixes against the cell wall to provide that durability. Because one of the things that the concrete lobby and steel lobby has used against timber is the fact that it isn't durable in their state of mind. It's high maintenance. Back in 1960, over 80% of all bridges built in North America were timber. By the turn of the century, that number had dropped to less than 1%. Today, there's around 25,000 bridges in service, counting PED, rail, highway in North America, of which 245 to 265,000 bridges are timber. Union Pacific on its own has about 38,000 timber bridges in service today. And so there's a lot of timber bridges out there today. What are they doing with them? Repairing them and taking them out and replacing concrete. When I went to school in the late 60s, early 70s, we were entering the great panacea of precast concrete. They told us that because concrete lasted a long time, everybody would say, well, look at that concrete sidewalk. It's been there a long time. You just can't build bridges with timber because of the high maintenance, they don't last. Everybody was forgetting this important detail. And that's it in most of the G10 countries. The average age of a timber bridge is 82 years. Well, if they didn't last, how are they going 82 years? What they were really saying is that they're higher maintenance cost. And where did the maintenance cost come from? It came from poor detailing. The use of vertical fasteners that originate from the top, allowing ambient environmental moisture to get to the inside bright zones and work their magic with decay. And all we needed was over 21% oxygen, over 22 to 24% moisture, temperatures between, say, 40 and 120 degrees F, and we had decay happening in untreated bright wood. In Florida, where I live, we have 365-degree hazard days a year. So if you're not treating timber or designing it correctly, then it's not going to last, and it has a high maintenance cost. And that's what the concrete industry hinged on and convinced people to switch over to concrete. And that's what they did. Well, guess what? Now concrete has got its own Achilles heels, as we're going to start to see here in a moment. And timber is making a big comeback, particularly in the mass timber form, as you can see here in this beautiful 10-span bridge. This bridge in concrete was $15.6 million. In timber and mass timber, it was 4.2. I mean, that's a significant difference, and one that drives the equation now. As you can see in these mass timber bridges here, these mass timber bridges are going into service, doing the job. And how is that happening? Well, this bridge here on the left is completely pre-assembled, including a TL4 truck crash-proof rail system in Jefferson, Oregon, and then completely taken apart, lettered and numbered, treated, shipped to site, and the bridge on the lower right is the one on the upper left. And it combined the old timber elements used in the past. And you can see something very unique in this bridge on the right is there's no concrete, not even concrete in the substructure. We hydrojetted out the trenches and dropped the sill down on pea gravel compacted below frost line and built the whole bridge out of timber, including the substructure. And because of the naivety, the district chief engineer for highways in that area came to me when he looked at the prints, and he put a great big red line through our structural IFCs. And he said, you can't build timber bridges anymore. They're not allowed in the code. And I wrote back, I said, I can't imagine what you're saying, because I'm on C9 and S6, the Canadian Highway Code, and I've been involved in ASHTO for many years, and there's timber bridges allowed in both codes, and I'll see at the bridge site. Well, we arrived at the bridge site. He was there. He looked at this bridge, and there was no concrete. He said, well, you can't build a bridge without concrete. You have to have a concrete substructure at least. I said, why? Show me in the code where you're not allowed to put a bridge in place unless it's on a concrete sub. It's not there. It isn't there because it's not the truth. The fact of the matter is that timber can perform well in not only superstructures but substructures. One only needs to look at all the timber piles driven for bridges around the country. Obviously, it doesn't have to be on concrete. This bridge here was relatively new in the last 10 years. It was completely pre-machined, pre-assembled, taken apart, post-treated, lettered, numbered, shipped to the site. And of course, we compacted and put down an abutment bent instead of a concrete bend, instead of cast in place. This bridge went into service in about a third the time. Why? Because we didn't have to wait for concrete to cure. We didn't have to carry 8 times the dead weight, and we could put it into place such that this bridge from start to finish was 21 days on the install. The concept of doing that in concrete on a heavy L100 ton bridge, which this is for forestry haul, it just wouldn't happen. So this is the other place we see timber really shining. Well, people said, Dan, timber just doesn't last. Well, man, let's take a trip down the memory lane here. This is concrete that's supposed to be lasting. This is the largest civil infrastructure disaster in Canada, is Gardiner Express Parkway. And what they had to do was spend $1.8 billion to fix bridges, concrete bridges with an average age of 32 years. I'll say it again, $1.8 billion to fix concrete bridges or replace them with an average age of 32 years. Precast installed, they'd already tried to fix this drummy concrete problem by doing overlays one time and couldn't get there, as you can see here. I mean, what do you do with this? Where does the drummy stop and the good stuff start? It's virtually impossible. This does not happen with timber. The diesel off of trucks doesn't mix with chloride-rich environments and create a disaster for the concrete. Timber just doesn't rust. And so timber is a preferred choice for that. Well, how about steel? You know, you can only do so much structural painting to try and keep rust away. What's this guy? Rust-resistant steel on the coast of Georgia, 18 years old. We can't have that in our railway bridges because this happens. So we go back to timber. And this is where mass timber is really coming in. Well, people say, you know, show me evidence, Dan, that timber lasts. Well, this is the 200-year-old bridge in Russia with no nails. As you can see, the timber bridge still in service. The one on the right, Qingdao, is in, of course, Japan. This bridge has been in service for, what, 400 years, 500 years, and a long time at that. Timber bridges have been around since the early days of Caesar before Christ. As you can see, are different old bridges. And this one I just showed you, Qingdao, what we call a leaf spring bridge, has been around a long time with spans of 35 meters each. You can see why they call it a leaf spring bridge. So, you know, people say, well, these timber bridges just don't last. This is in northern India here, for example, where bridges aren't built, they're grown. And this one is 647 years old, grown at a Ficus benjamina. The people liked it so much, they're having so much traffic on it, they grew a double-decker bridge, as you can see here, to get the traffic across it. And this guy here, they grew the handrails. And why are these bridges lasting 640 or 700 years? It's because they're growing their connectors. And these connectors mean that we don't get moisture to the inside bright zones of these timber pieces, allowing decay to take place. So that the same thing can happen when we build them. Now, these are new bridges now in the last 10 years all over the world. I'll just show you. Look at these spans, 47 meters. That's a long span, close to 200 feet. You see another one here. All over Europe, we're using these spans. You can see them here, creating long span bridges, replacing concrete and steel because wood doesn't rust. And if you find ways to keep the moisture out of bright zones in the interior portions of your timber elements, they're going to last a long time, as you can see here in these various photos. Beautiful timber bridges, building roofs over the top of them to keep water off of them, to keep them going the distance, as you can see here. This one in New Jersey, similar. Putting them together in bits and pieces and keeping them going down the road. This one here was 10 tons. It was an old timber bridge that had a MPP deck on it, was not treated. Of course, the vertical fasteners got in through the top, let the moisture in. It was 80 years old. It was time to go. We had a community, an island community that would have been landlocked. A bypass bridge was $2 million. A concrete bridge was $6 million. And so in 11 days, they built a floating scaffolding and replaced this bridge piece by piece and put her back into service in 11 days to get where they're going. What was different? No vertical fasteners from the top and no treated. That's a eucalyptus hardwood chosen for its durability with stainless steel clips from the bottom and everything originating from the bottom, but not passing through the top surface, as you can see here, with expansion slots in here to allow the deck to shrink and expand as it picked up moisture. As you can see here, with gauge beams that provide for differential deflection to keep the asphalt, of course, from reflective fracking. So you can see here in this particular case, this is in the jungle, way up close to Papua New Guinea, where they are putting in a new timber bridge in a very harsh environment, the highest decay hazard zone, the highest termite hazard zone, the highest embedded and exposed corrosion zone. All of these factors would normally lead one to consider putting in a concrete bridge because they'd say, well, it's got to be durable. Well, the timber can be durable too, to create a great solution for this bridge replacement. With thrust rods, for example, to allow us different spans. And this bridge was built in Jefferson, Oregon, and shipped halfway around the world into the jungle to be installed. Why would we do that with timber unless they were confident? Why? Well, they're confident because they like the carbon aspects, they like the durability aspects we can create today with new technologies and new concepts. Same one goes with this. This is in the west coast of Australia, an old timber bridge that was 100 years old, and the community wanted to keep that timber bridge in service. They didn't want to take out the history of the past. And so we developed a restoration system that took out these old vertical fasteners in the deck and put a new deck down. And we didn't heavy coat paint the large dimension timber. You can't put heavy percent solids, over 29% solids coatings on large dimension timber outdoors and expect it to last. It has to be less than 29% solids if you're going to see it last. That looks like paint, but it isn't, as you can see here in this whole new system. And you're turning the rails 45 degrees so that everything runs off, keeping the proper scuppers and no verticals in that whole system. And our design kept that bridge open for traffic while they upgraded it. So the advantages of timber bridges are pretty important to note. A typical, on average, 1/8 the dead weight for an equivalent structural capacity concrete bridge. This allows smaller substructure and subsequent cost savings on the foundation and site works. On long spans, self-weight of concrete becomes the biggest design factor. One of the greatest things I like to do as a designer is get involved in a long span design, 79, 80, 100 meters, let's say 350 feet clear span, use high strength fiber, because I know in that particular case, the self dead weight of concrete is going to be their biggest single design factor, and that's where they are just not in their sweet spot. Typically, the sweet spot today for concrete is in the 50 to 75 foot clear span, where the CIP abutments really don't have to be modified that much. When you get over 100 feet with a clear span, concrete is just not economical. So why do we see all the concrete bridges in America? I mean, I go to the airport here in Jacksonville. I drive under a new interchange that's approaching $650 million. Everything is concrete. Why is that? Well, they won. They convinced the industry in the early 60s that they outlast timber and their lower maintenance. And that's when we're winning back now with MassTimber in our concepts as we work around the world with designs and convincing these people that this just isn't the case anymore. As governments start taxing their citizens for carbon, it would behoove us all to think about timber bridges, MassTimber bridges, when they're 21 times more carbon friendly than steel and 16 times more carbon friendly than RC. If we're going to tax citizens for carbon, we got to use carbon-friendly materials in the construction of our infrastructures. Rapid installation is one of the other really big features about timber bridges. I mean, I can't tell you enough how this rapid installation bridges, this was 2 tracks of rail from the time they de-electrified the electric line here at 7 o'clock on a Friday night till the time cars were driving on that bridge on 9 o'clock on Sunday evening. That's high-speed bridge work. Lifted into place and fully assembled, 2 lanes, an 8-foot wide sidewalk, completely pre-assembled, lifted into place. And this crane that lifted this full 2 lanes, 60 foot long, that with an 8-foot wide sidewalk, that whole assembled bridge weighed less than 1 precast concrete girder of the same span they lifted in the week before. And we did this bridge complete in 2 days. See, this rapid installation is a big feature of wood and low initial cost. Traditionally, the minute we exceed 100-foot clear span, traditionally, the cost of the super end deck starts to migrate down to be 60% less than concrete and 30-some% less than steel. Reduced carbon emissions is a big, big feature, significance, 21 for steel, 16 times more effective than RC, as you can see here in this particular bridge. With the look of the savings here. That's a metric ton savings. That's a lot. So these chemical resistance features are really good too. We often talk about salt on the road up north or salt sand mix up north on the roads. And this salt really works a magic on reinforced concrete. That chloride-rich environment takes it out easily with spalling and other issues related to reactive aggregate. Well, that chemical resistance of wood is one of its big features. In fact, in a salt-rich environment, because the salt will neutralize the acidic contact of a pH wave in a decay colony, actually helps improve longevity. In some parts of North America, they actually sprinkle rock salt on their timber deck bridges in the spring when the water can flush that salt down into the wood and extend its life. So just the thing that creates a chemical problem for concrete and steel creates an advantage for timber in use. And of course, resistance to freeze damage. We all know that wood has a much better freeze thaw cycle resistance than concrete. Fatigue resistance. We don't need to use a fatigue factor in timber. In some countries, like Australia, where the timber code portion of the bridge committee has been controlled by the steel guys, they artificially put a 2 factor in for fatigue for timber, which doesn't even apply. We still have some codes in Europe specifying expansion joints in timber bridges. Wood doesn't expand thermally enough to require a joint. There's no expansion joint required. The only joint needed is for differential deflection between an abutment and the timber deck itself. So where do I work? I work at Wood Research and Development. We're a code-approved test agency, third party and testing. We're also an American Lumber Standards Committee test. We have a commercial engineering wing. We do a lot of testing and design. We developed advanced fiber solutions. This is one of our big areas that really feeds into mass timber today, using high strength fiber like Kevlar, particularly, which matches well with wood because of its thermal coefficient of extension properties. And using these high strength fiber in a way to basically transition by localized defects in the wood, like slope of grain created by knots, for example. I have a few patents in this area, over 40, I guess. And I developed ways of doing this using Kevlar and carbon, pre-tensioned, cured up into a high-strength fiber solution, as you can see here with the backfield pre-tensioned here on the right-hand side that dips through it in a tank, gets saturated with a resin, kick over the catalyst in a heated die, turn into reinforcements of various lengths. So now you can have high-strength fiber on a roll. You can have up to 2 miles if you wanted on one roll. You use it and cut it off in certain lengths. You put it in strategic locations. It's 5 times the strength of steel at a fifth the dead weight and matches things well. And it's been in service a long time, and it's in the ASTO standard, and it's in various codes around the world. It all originated from my design principles back in the 80s and 90s that developed. As you can see, this first one in this first highway bridge in America, built in 1995 in Clallam Bay in Washington State. In service since that time, doing a great job. You can see the high strength fiber here, doubling or tripling the moment capacity. And through fire test, we put it through for both single member and assembly methods. 121, heated up to 1500 degrees C in 5 minutes and watch it burn, measured the deflection, and established fire resistance ratings, as you can see, for single member and for assembled members, as you can see here, FRRs in minutes. And one, of course, the great things for high strength fiber is, what does it do? Increase the moment capacity by 2 and 3-fold, allowing us to get 2 and 3 hour fire ratings out of our timbers because of increased moment capacity. We often say, well, wood's governed mostly by stiffness. Well, that might be true, but moment's close behind, and what drives egress and access in fire scenarios is moment, and being able to increase its capacity with high strength fiber that way by giving yourself more time is very important. Of course, testing in our lab has formed a huge part of it, with over 3,000 full-scale beam tests over the day, including strain gauge data all the way across this to establish where shear is a maximum, for example, and so on. So you can see the size of our beam tester in our lab. We do some big beam tests and small ones, and pile testing. As you can see here, strain gauging pile wraps. We developed the Fiber Wrap 2 product that Osmos use on the utility poles. So this full-scale established testing is there also to look at things like horizontal shear. 65% of horizontal shear failures upon the late wood, early wood interface in wood. And so how do we gauge that and deal with it? Well, you can have high strength shear replacements as well, increasing the shear capacity of a piece so that we strategically design these mass timber bridges now to be fine-tuned, to have strategic location of advanced materials to handle shear, strategic location of advanced materials to handle high tension zones. And this allows us to post-treat and get where we're going. You can see here the fiber on the right, reducing 42% of the wood fiber needed. And the wood fiber used is all low grade, as you can see here. The one on the left is equal to the strength of the one on the right. And we just basically reduce the variability, which increases the capacity too, by reducing the amount of premature failures due to slope of grain, due to knots. You know, you get knot in the bottom face of wood, it creates a slope of grain. Wood's tension to perpendicular to grain strength is its weakest Achilles heel. When you resolve the stresses around this knot in the slope of grain, that's what causes the failure. That's why we don't like big knots in the bottom face if we're at the solid sawn elements or in our glulam beams. So there's a dichotomy of high strength fibers that are available out there today. Everything from quadraxial tribrid wraps for piles to high strength fiber and tension, and for shear panels and off axis shear. So we do a lot of this testing, as you can see here in the lab, and we develop wraps, as you can see here, for utility poles and piles. We do compression tests for these to establish what capacities are with both the wraps and the injected slow cure epoxies that are used to fill voids, for example, in the restoration of old structures. And this then allows this implementation to mass timber bridges, these high strength fibers, to fine tune this to make us more and more competitive with steel and concrete. Today, just so we understand, this isn't about initial cost. If it was about initial cost, every bridge being built in America today would be timber. This is about a victory they won in the 60s, 70s, and 80s to convince an industry that timber didn't last and had high maintenance costs. We're about convincing an industry today that that isn't true, that you can build these bridges out of timber and use things like shear panels to get where you're going. Not only in shear panels from the point of view of minor axis shear issues, which you can see here in one of our test setups at the lab, where we developed a way to increase the minor axis shear for platform framing of mass timber versus post and beam framing. As you can see here, the placement in these CLT systems of high strength fiber on the tops of the columns to deal with transverse or rolling shear issues which exist in CLT, as well as mass plywood panels. That rolling shear issue, which is as a result of the weakness of wood in cross grain to shearing, as you can see here. So this is shows you a reinforced panel that gets placed on strategic locations in CLT and mass plywood panel to get where you're going, to take this system to this system and get where you're going with thinner panels in this system. Well, that works over in bridges as well. This is a wood welding situation where we ship the pieces of wood in 17-meter or roughly 60-foot length, and then we assemble them on site and basically use high strength fiber for continuity to be able to assemble any length. You can see this is just one portion of a bridge here. It's going to be 3 of these to make the full length bridge, as you can see here in this picture in the lower right, with reinforcement strategically placed where the high strength, where it's needed, where the stresses exceed the capacity of the piece at that location, to keep the size of the beam smaller, to keep its ability and agility to go longer intact, as you can see here on the right-hand side at the bottom, as you can see this reinforcement showing here on the bottom face of this girder. In rolls to be unrolled and used in strategic locations. This has advanced the use of timber in bridges more than perhaps any other development in the last 20 years to get where we're going with a lot better capacity. You'll see here the placement of this RP and its particular zones. You see it here. So we'll use this to do wood welding. As I said earlier, the wood welding is a big feature today with bridges because you can't ship things in America over 60 feet. So, you know, how are we going to make a 380-foot long bridge? Well, we're going to wood weld that together and on site. We pre-machine it in the factory. As you can see here, all the shear plates are pre-machined. We're going to take these pieces of timber and we're going to put them together with strategic strategies that involve everything from shear plates, shear pins, doweling, to side plates, bottom splice plates. They infill all the cavities around the split rings and shear plates, depending on what's used. They're all infilled with structural epoxy so that there's no slip distortion We don't want slip distortion at a joint in long span beams. And we use thrust rods to pull it together to get the 125 PSI that we need on a butt-to-butt joint. And then we basically create a wood weld at that location with high strength fiber. It's equal to 125% of the wood's capacity in any other location, as you can see here. This is new technology, new concepts that are creating mass timber bridge opportunities that we haven't had before in the industry. You see this piece of Kevlar here with a design capacity of 215,000 PSI to strategically place this in certain locations gives a huge advantage. And why is the steel completely saran wrapped? Well, you can't marry up steel with wood and glue it because steel's thermal coefficient of expansion is so significantly greater than wood that modest changes in temperature are going to create a blowout in that steel plate, and that it will basically lead to expansion that exceeds the pilot hole size in those particular plates and create distortion in the connector and create lateral loads on lag screws, for example, in the splice plates, as you can see here in the bottom face. This wood welding is a serious opportunity forward in the competition with concrete. When I can go 4 beams at 60 feet apiece, 240 feet long, when I create that beam out of timber, it weighs 1/12 the dead weight of the concrete, costs 60% less than the precast concrete girder, carrying the same loads, truckloads, as the concrete. This is what vaults timber ahead of concrete in these locations. This particular bridge, called Dillman's Bridge, was $6.2 million in precast concrete and CIP abutments, CIP deck, cast in place. And this bridge here, built out of timber, was $3.2 million. Those are significant savings that create the opportunity. Well, concrete immediately comes back and says, well, you know, timber burns. Well, I don't know if you ever know this, but if you put concrete in even a low temp, you've got to inspect it. You got to watch for expansion of the rebar. It can blow out the rebar couplings. In timber, when you get large dimension pieces, it chars, or if you want to protect, you use an intermissant. And today we use intermissants on our timber when they're in the fire-prone areas and get the extension of life that we want and the protection against bushfires and so on, as you can see under this bridge here. So we won it's not to brag about this, but in 1996, we won the Charles Pankow Award for Innovation for this. And then 97, won the Nova Awards, first time ever won by wood. We were up against the steelless deck system in the first award. And for all construction products, of course, we were up against mostly concrete and steel competitors for those awards. And timber won those awards. At our lab, we do things like species identification. We take cores from old bridges, as you can see here, and we identify the species, we identify the grade, we identify moisture contents to establish things like, for example, the average moisture content in a closed deck timber bridge is 14.2%, not close to 22 to 24, the decay point. And in an open deck bridge is 16.4%. Again, not close. So why is it that the moisture content in the average bridge today in America is that low? Why is it that decay is the #1 killer? 80-some% of all timber bridge degradation is due to decay. Why is it? It's because of our vertical fasteners. It's because of the way we design and do things. So we get in with our lab and start doing these assay samples. We identify species, we identify grade, and we tell a client what's going on in their bridges as we work this way through with these species identifications and grade identifications. We do testing at the lab to establish the capacity, for example, of step dowels, as you can see here in the lower left, that join wood together. We'd have training programs where we conduct courses. There's 16 courses, level 1, 2, and 3 in each of inspection, maintenance, restoration, and design. And these courses are part of lifting the game in the business today. I head out just in a couple of weeks to teach a level 1 and 2 course up in Northern Australia about timber bridges, for example. And what is that about? It's about passing on knowledge, what we know. It's what we call heredity. And that's my big brother told me. Well, that's what we like to do in the industry, is help people understand, because a rising tide brings all boats up. If we can show people how things work, I'll help them understand how timber works, then we won't build bridges that are high maintenance costs that don't last. And we'll take that hook out of concrete and steel's hands and put it back in timber's hands. So we're heavily invested in training people around the world. I've I guess probably in my career, some 4,000 students have gone through my courses now, where we teach them everything from high strength fiber wrapping of piles to how to diffuse wood using naturally occurring salt rods, and how to make sure that if you ever wrap a timber pile, you've got to allow for expansion, because capillary action brings water up in that pile and expands it, and it'll put a lot of hoop stress on the RP. And the fact that you must use a diffuser of some kind to protect that wood, because that moisture will come up over 22%, 24%, and lead to decay in the interior bright zone. As you can see here, this training on timber covered bridges that I taught, or this one in Portland on Tudor arch bridges and girder under bridges. So this leads to these sorts of certificates that we issue to people who take our courses, and education is a huge part of what we do. We also write books. This is one that Greg and I wrote on Guide to Wood Construction Systems, as you can see here, where we talk about everything from multi-floors to Tudor arches to dome buildings on the top of timber buildings. Who would ever thought, when I graduated back in the 70s, that I would be writing a book about having a swimming pool on the 18th floor of a 20-story MassTimber building? I mean, we are way beyond what we thought about the day. How about charring? Who would have thought we could use high strength fiber to increase the char resistance and increase the capacity such that we could have a fire resistance rating of significant amount, 2 and 3 hours in a MassTimber building. Another book that we've just recently written, that's just been released, is Timber Bridge Inspection, Maintenance, Restoration, Design Detailing Guides, 956 page 3-volume affair, where we talk about everything under the sun. As you can see here, timber bridges, detailing, restoration, and advanced design considerations, whether it be load sharing and large dimension timber elements, which are now develop load sharing factors of 1.2, for example, or whether it be talking about shear, the fact that at the reaction point, the shear max drops close to the bottom face. That's why we can neglect shear distance D away from support. It's not at the neutral axis. And we show that in a continuous piece that moves up, why we have to be careful of shear in continuous beams, because we can't neglect shear distance D away from the support because of that factor. Listen, we often say that good wood is gone and that it's harder and harder to find quality wood. But what we don't really realize is that the good wood is still there. Wood grows the same way it's always grown. You know, in the petrified forest in Arizona, there's a bunch of Doug fir logs that kind of fell to the bottom, covered with ash when the great inland ocean receded, and they were mineralized and basically petrified. And they've investigated and found out that these Doug fir logs grew the same way 250 million years ago that they grow today. So when we hear this term, good wood is hard to find, it's gone, what we're really talking about is that the big boxes like Home Depot and Lowe's and others have put downward pressure on our grade standards. They pull a premium grade because they don't want to put a SKU number on somebody's 2x6 and have them pick through it and leave the bad stuff in the bin when they go Saturday to buy a 2x6. So there's pressure on the grades. We allow 5% off ball on the grade, but they put pressure on it. So what we're really meaning when we say the good wood is hard to find is that the different ways we grade has led to us to consider things like engineered wood that allows us to use machine and reman to get the distribution of defects to increase capacity. And what CLT has done is put that in a way that involves less reman, because we can use solid sawn now and cross ply it to take this Doug fir piece and turn it into solid sawn wood and run the CLT from it to form a mass timber. You know, softwood trees are geotropic. They grow in response to light. To gravity. Hardwood trees are phototropic. They grow in response to light. So the Achilles heel of a hardwood tree is slope of grain. That is not the case with softwood. It's why the northwest part of the United States became the wood basket of the world. You had a specific gravity of 0.48 to 0.52. You could nail it. You could cut it. It had good slope of grain properties, and it was strong and lightweight. Well, that's the way we want to deal with wood today, is that consideration. Not to use the term the old growth stuff is gone, but to instead consider timber in its regen fashion, and the fact that we can use it in a variety of ways by using advanced materials with it. I often like to look at this one at Tillamook Air Museum inspection. This is one of the 7 construction wonders of North America. It's 22 stories high. It's 260 feet wide, 1,000 feet long, made with 3.5 railway trains loads of wood back in the Second World War when the steel was going to bullets and tanks. And they built it out of timber. And they sailed 8 blimps in there that were used for the inspection for submarine detection on the Pacific coast. And now it's used for an aircraft museum, all made from timber. Well, this was in the 1940s. This was the mass timber edition of the 1940s. Wood hasn't changed much in hundreds of years. It's how we use wood that's changed. That's what's caused the difference today as we put wood together in different ways and market it in a way that allows us to get where we're going, such as this Keystone Wise Bridge. This is one of the biggest timber interchanges in the country, made out of glulam beam. Well, they had put concrete deck panels on it, were heavy, they nailed them to the top, and the only place that they could find any decay was where they put verticals into it. We came in and said, well, let's save this bridge. It was built in '66 out of Doug fir from Oregon, pentachlorophenol treated. It was in great condition. So let's put it back into service. So we used high strength fiber, put it on the bottoms of the girders to double capacity. We changed the concrete panels out to vertically laminated glulam deck panels. That reduced the dead weight on the bridge by some 75%, which increased the capacity just by changing out that dead weight and putting the high strength fiber on it, and put this bridge back into service by paving on top of it. And there it exists today. That timber bridge is set for another, 50 to 100 years. So this is one of the big ones I always like to talk about because it was where we won some awards. It was a 3-lane design, the longest 3-lane design in Canada, called the Roger Bacon Bridge. I won several awards for this bridge. And it's not that I'm winning awards is the big thing for me. It's why we won that I want to talk about in this particular case. The why we won. This bridge was built in steel. That we replaced a timber bridge in basically 1940s, late 40s, with a steel bridge in the highest embedded and exposed corrosion zone in the country. And this bridge that was there was built in steel, and this is what happened to it. This steel bridge was installed on old piles that in the 40s were already in service for 90 years. What I really loved about this was taking this new lightweight timber bridge, replacing a steel one, using the old piles that had been there already for 90 years old. When they were installed, they were 180 years old. They're basically containing embedded carbon. We're using a carbon-friendly solution to go on top of them. We use pulse echo technology. We used mud shock to strategize if there was any decay. Down below the oxygen, the piles were as good as the day they were driven. We healed up the tops of the piles and built a new mass timber bridge on top of those piles. And that entire processing of the new bridge was done in advance, machined and assembled, taken apart and lettered and numbered, treated, built on site, and lifted into place. As you can see here, this huge long span lifted into place and dropped down onto these new caps. And who would have thought that we could put a 500-ton gull wing crane on a timber jump span that was finished 7 days before? Could we drive a 500-ton gull wing crane out on a CIP concrete bridge that was finished 7 days before? Not mighty likely. If we tried that, that crane would be sitting on the ground. And that timber bridge carries that crane and basically allows us to lift that 3-pinned arch across into the gap and form up this beautiful bridge, which led to another bridge like this one getting built, which was going to be concrete. And this bridge come in the same way. Why? Because the client saw it was a great solution, lower cost solution by 35%. And this is why we're seeing timber bridges come today. As you can see here, beautiful timber bridges, mass timber bridges built. This one 35 meters, that's a long span bridge with timber piles driven, with frost jackets so we don't see frost jacking on a taper jack, with specially designed boots to go into certain types of soil like clay or boulder till or different types of soil. This is the old boot that we'd see 100 years ago, straps and a point. This is the new boot today, involving new technology and concepts to cause these piles to drive straighter in the ground. You can see here, they all form in a line. Look at that. So the cap goes on in the right way. That's a long span. That bridge in this span was 6.35 million in concrete. In timber was 3.9. I'll say that again, 6.5 versus 3.9. Why aren't we building all of them in timber? It's because of this perception that timber doesn't last. And we're about changing that. This province in Canada, for example, now has gone from letting rural highway bridges be spec'd in timber. Now they're considering letting concrete bridges that are going into their Trans-Canada type bridges being spec'd in timber, as you can see here in this beautiful bridge. Another 25-meter span one, the same thing. Mass timber bridges moving into the industry, as I showed you earlier. Mass timber being pinned to the rock outcrops, total wood, everything's wood, including the abutments, all designed and built with this in mind. And the people love these bridges. They're aesthetically pleasing. They're lovely to work under and be around. This bridge right here is a new one. I just put this one in. As you can see here, this is a mass timber bridge. It's built on basically a 450 fan situation, 450. It's going to be a light vehicular pad bridge. It's there with a tidal zone that the river flows both ways. It's a tide zone. We simulated the natives of the time, the early Indian settlements that were there with a lot of the sweep. We put it into rise and fall. These are the concept drawings here. But I wanted to show this as I bring to a close. Look, people say, well, Dan, you're always blowing smoke about this being a big saving. Look at these numbers. These are concrete and steel numbers along with timber numbers. And take a look at the bid prices. This is a public domain, public bid. These are the closing date costs, June 2nd, 2025. That's MassTimber, WRD, TRS, MassTimber, 7.9 million. The one at the top below this, you talk to the Caldwell, those are all typical concrete and steel cost points for those tenders. And you see the difference. I rest my case. This is where we're going today. We're going back to timber in our bridges. And this is where we want to be. We're going to win because we're economical, we're carbon friendly. In the pan bridge that I just showed you about up there, that 3-pinned arch bridge that I showed just a little earlier, we won the award for. In steel, it was plus 2,760 metric tons of carbon. In timber, it was minus 970. Plus 2,760, minus 970. That's a carbon advantage. It's a cost advantage. The bridge itself costs 33% less than steel, has a design lifetime of 100 years, carried 62.5 tons just like steel. Timber can get it done. It's just all in the design. It's how we plan and how we do it. It's what we do in our design side that helps the timber go the distance. Don't disadvantage it with connectors from the top, for example. Don't go there. And basically build that timber bridge in the correct way, and it'll go the distance. With that, I bring her to a conclusion. I'm sorry you had to put up with me for that length of time. I'll be open to questions. Thank you.
Dr. Dan, timber can get it done. Thank you so much for
Go
your
timber. That's
fascinating,
me.
insightful, go timber. Your fascinating and insightful and also very inspirational and thought-provoking presentation to our Michigan Mass Timber community of practice. Outstanding.